So welcome, this is the third tutorial on I2C. So in this tutorial I'm going to be explaining core signals and how they are being generated. So first of all, let's talk about the gen. We are going to talk about this gen. Remember I told you the master slave, what it does. If it's 1 is a master, if it's 0 is a slave. The BB means boss busy. It turns on whenever the bus is busy. Detect stop is used to detect a stop condition. So then the gen stop is used to stop the master. So this master slave sig. So throughout the code you are going to see this value sig at the end of some signals. Sig, whenever you see sig, is the same thing as the master itself. Example, this master slave signal is the same thing as master slave. That is, this master slave sig and this master slave are the same. At the end of this code we are going to join them together. So the sig are more like how they are being generated, that is their output. And when you name them master slave, it means when they were used as ordinary inputs. Whenever you add sig to it, it means where they were generated. So it's more like how were they generated. So it is when you have sig to it. So let's first of all talk about this gen stop. How do we stop this gen? So first of all, to turn it off, that is to set it to 0. So see what sets it to 0? Detect stop. So whenever there is a detect stop signal, this gen stop goes back to 0. But let's see how it's being generated. 1, this signal needs to be off. So what signal is it? Let me trace it down here. Oh, quite far. Ouch. Arbitration lost, and this one negative mode sign. Okay, no. Okay, let's see this. Let's talk about gen start first. So you before we go back to gen stop. So to turn on gen start, okay, detect start and detect stop. Gen start is used to, the difference between gen start and detect start. Gen start is used to generate the start signal. That is if you are using the outputs of the SCL and the SDA, while detect start are used to detect them. So when you see detect stop, detect start is for the SCL in and the SDA in, detects them, whereas the SCL out and the SDA out are used to generate the gen start and the gen stop. So see, in this scenario now, when this gen start is on and you detect that is on the next clock cycle, set it to 0. So what is trying to say is that this gen start is not going to be latched. Whenever it comes on immediately and it gets detected using the SCLN and the S. Okay, once you use the SCL out and SDA out to generate a start condition, this gen start signal comes on. Yes. Now, whenever is on, the SCL in and the SDA in is going to detect it, and therefore this detect start signal comes on and turns it off. So the gen start signal is more like a single pulse signal. Yes. So this positive mode signal actually detects the start signal, whereas the negative mode signal detects the stop signal. So as you can see, once this negative mode is used to turn this gen stop on, while the detect stop means is that the gen stop is on already, detects it and then turns it off. So on the next clock cycle, turn it off. So negative mode signal is used to start it. Positive mode signal is used to start the gen start. So those two, see where they were being generated, the positive mode and the negative edge mode. Remember I told you the signal means is still the same thing. So whenever you see this and this are the same thing, then these two are the same thing. So whenever you see sig at the end of a word, you can as well remove it. So that's the convention used here. So something like this, you can as well remove this. Wherever you see core counter enable is the same thing with this. Wherever you see stop SCL is the same thing with this. If you see this is the same thing as the SDA out. So this sig is actually a variation of it, but it doesn't do much. So this is the positive edge mode and the negative edge mode. These are them here that were used for the gen start and the gen stop. You can see the detect start, detect stop also. So how does the detect start work? How does it know? Remember the start condition says whenever SDA is low and SCI comes high, right, we have a detect start condition, or more like our normal start condition. This is it. These are where they came from, the SDA in and SCL in. So whenever it detects it, this detect start signal comes on, and then remember whenever it comes on it moves to state 1, and whenever it goes to state 1 turn it back to 0. So this signal here, so all these detect start, detect stop, gen start are actually pulsed signals. So this signal here is the SCL main state we talked about. You can see it. This is it here, the SCL main state that we've been talking about earlier before now. So I hope you are understanding this. So what it's trying to do here is whenever it goes to state 1, set it back to 0. So when it's in state 0, it comes on, it's used to move it to the next state. While it's forfeit, this is the start condition here, SJ in and the SCL in. Once it detects it, move to the next step. So you have this signal again. Let's talk about this byte trans sig. Byte trans signal means that data reception has been completed. Now let's see what turns it on. What makes it on? It says when bit count is equal to 8, and whenever the bit counter is counting, it starts counting at the start of reception. You know the data are usually 8 bits wide. So once it counts 1 to 8, it knows that it has received 8 bits of data. Therefore, turn this byte trans sig on. So that is how this byte trans sig comes on. Now we have this BB sig. This BB sig, I told you earlier, means bus busy. Bus busy. So let's just see what turns it on. Let me highlight it. Let's go. A detect start condition. Remember, detect start occurs only once. On the next SCMN state, it goes back to 0. So this, once the detect start turns on, it sets this bus busy on and lashes it. So this bus busy signal is going to stay on up until the end of the data transmission before it resets. So let's see what actually resets it. One is the normal reset here, and 2 is this. Let me go up and see. A detect stop. Can you see it? The detect stop is used to turn the bus busy signal off. So that's that. So another signal, let's talk about this area. This signal, slave address sig and the address match. So what is this slave address is the address of the slave, assuming we are operating in a slave mode. We already have our slave address stored, and remember that the first 8 bits is going to be the address which is going to be sent by the master, and it's going to be stored in this address register. We're going to talk about the register in the next video, address register. So what it does is it compares our slave address with the received address in the address register. If they are the same, once they are the same, it's going to turn on this, and this signal slave address is going to go over here. So it's going to turn on, and it means that the slave has been addressed. So this signal is going to turn on to 1. I don't know if you understand. Let me remove all this, and note you what is being addressed. This is 7 down to 1, not the full 8 bits. Remember that the last bit is used to say are we reading or are we writing. So here you can see there's a splitter here. It means address 7 down to 1. That is what is comparing, using that comparator. So this here, so let's see what when it checks for this. I've highlighted what turns on the multiplexer. Remember bytrans, I told you that the bytrans comes on once the data has been received. So this bytrans is used to turn on this multiplexer for comparing. So whenever this bytrans signal, that is, it has received the whole 8 bits, the bytrans comes on, and when it comes on, it turns on this multiplexer here and checks is the slave addressed, or it compares the received address with our slave address. If they are not equal, it's a 0 is equal to 0. So a 0 is going to come here and say that the slave has not been addressed. If not, if it has been addressed, it's going to come on 1, and we are going to have a 1 signal here to show that. So that means whenever this signal turns on, it means that the master wants to speak with us. That is, our slave address and the address in the address register are equal. So at that same time, this bit also comes in, the address match bit also comes on. That is, if it gets energized, it's going to take 1. Address match, it means that the master is actually communicating with the right slave. If it's not, it's going to be discarded. So looking for, let's talk about major signals to talk about. So let's talk about this bit count enable. Remember, I'm not going to touch all the signals. I'm just going to talk about the core signals you need to understand. For then when you are going through the code, everything will be clear to you. So let's talk about this bit count reset and bit count enable. Remember, we have a bit counter that counts up to 8. So when does it count? How does it count? So let's talk about that. So it counts depending on what state machine we are on. So what we're going to check about is bit count, this bit count reset and bit count enable. So the bit count reset is when do we reset the counter, and the bit count enable is when we start counting. So this means states at which we count and state at which we reset. So first state is whenever I state 6, these are the states here: state 6, state 5, right? Yes. State 2 and state 0. So that is the state at which we reset, because it's a or. So state 0, that is initially when we are in the idle state, reset the counter. Then state 2 is after receiving the slave address. And state 5 and 6, remember 5 and 6 are the state which the SCMN state goes to immediately after reception and transmission. I forgot to tell you that this signal here is the SCMN state, which we talked about in the last tutorial. I just highlighted it. So these are the states which we reset the counter. So now let's talk about the states which we enable the counter. So they include, there are just 3 states, which are state 4, state 3, and state 1. Remember, state 1 is when we are sending or receiving the slave address. State 3 and state 4 are either when we are either transmitting or receiving. So we have to count to know the number of bits we have received or number of bits we have counted. So this is just to tell you that the bit counter don't count randomly. It has a time when it resets and starts counting. So remember, that is by convention we are adding 8 bits of data. So I think that will be all for this. In another tutorial, we are going to be talking about, now this I2C up is the received data. And the input comes from the inputs of this shift register comes from the shift. Remember when we talked about this shift here? So this is the shift. So whenever it's not receiving, this shift goes over and links up with this I2C up here. With this I2C up here. So this is where it comes from, shift reg. So they're going to be joined in another module. So that is that for this tutorial. In the next tutorial, we'll be talking about our controller interface, how the controller works. Thank you.